Hello everyone, welcome to physics class, standard 8, chapter 4, which is about work, energy and power. Basically, the chapter deals with work, energy, power and energy transformation, but the name of this chapter is energy. Anyway, in the previous video lecture, we discussed about work and energy, the various forms. The various form means about the mechanical energy, that is kinetic energy and potential energy. And now today we will discuss about energy transformation and power. But before discussing about energy transformation and power, first we discuss about some numerical problems related to kinetic energy and potential energy, and after that we will discuss energy transformation and power one by one. So let us begin. Example 1. If you apply 1 joule of energy to lift a book of 0.5 kilogram, how high will it rise? Consider the gravity is equal to 10 meter per second square. Gravity means acceleration due to gravity. G is equal to 10 meter per second square. So given that potential energy is equal to 1 joule, mass of the book 0.5 kilogram, and we know that potential energy is equal to mgh, or H is equal to potential energy by mg. Here potential energy is equal to 1 by 0.5 into 10, that is 1 by 0.5 into 10 by, that gives H is equal to 0.2 meter. So height is equal to 0.2 meter. Example 2. Calculate the kinetic energy of an object of 50 kilogram that is moving with a speed of 10 meter per second. Given mass of the object m is equal to 50 kilogram, speed of the object v is equal to 10 meter per second square. So using the relation, kinetic energy is equal to half into mv square. Now substitute the corresponding value of mass and velocity. Half into 50 into square of 10, that gives 5000 by 2, which is equal to 2500 joule. Example 3 is an important numerical. 2 bulbs of mass 3 gram each are fired from different guns. Bullet A moves with a velocity of 40 meter per second and bullet B moves with a velocity of 50 meter per second. Find the ratio of the kinetic energies of the bullet. Okay, so given mass of the bullet A 3 gram, mass of the bullet B 3 gram. Velocity of bullet A is equal to 40 meter per second. Velocity of bullet B is equal to 60 meter per second. So kinetic energy of bullet A is equal to half into mv square. Now substitute the corresponding value. Half into m, 3 gram. We convert the gram into kilogram, so it becomes 0.003 kilogram into velocity 40, square of 40, so that gives 2.4 joule. Now kinetic energy of bullet B, half mv square, half into 0.003 into square of 60, that is 5.4 joule. Now ratio of kinetic energies of bullet A by bullet B, that is kinetic energy of bullet A 2.4 by kinetic energy of bullet B, that is 5.4. So 2.4 by 5.4, that equals to 4:9. Example 4. 250 joule work is done to lift a bucket of mass 10 kilogram at a certain height. Calculate the height through which the bucket is lifted. Consider the acceleration due to gravity as 10 meter per second square. Given mass of the bucket is equal to 10 kilogram, work done on the bucket is equal to 250 joule. We know that work done on lifting a mass m through a height h, that is potential energy is equal to potential energy, that is mgh. So height through which the bucket is lifted, work done to lift the bucket by mass of the object, mass of the bucket into g. So 250 by 10 into 10, that is 2.5 meter, that is the required height. So now we discuss about energy transformation. One form of energy can be transferred into the another form. This phenomenon is called energy transformation. Some example of energy transformation are: when we rub our hands together, mechanical energy changes into heat energy due to the force of friction between the surface of our palms. When a torch is switched on, the chemical energy of the cell changes into electrical energy. The electrical energy on passing through the filament of the bulb changes first into heat energy and then into light energy. Means electrical energy gets converted into heat energy and light energy. In solar cells, light energy is converted into electrical energy. Here the solar energy gets converted into electrical energy. In fan, electrical energy is converted into mechanical energy. In plants, light energy is converted into chemical energy. In microphone, sound energy is converted into electrical energy. Similarly, there are many other examples of energy transformation. Often, transformation of energy involves a transfer of energy from one body to another body. For example, water at the top of a dam has potential energy, which is transformed into kinetic energy as the water falls. At the base of the dam, the kinetic energy of the water can be transferred to turbine blades and further get transformed into electrical energy. According to the law of conservation of energy, energy can neither be created nor be destroyed. It can be converted from one form to another form. This is the statement of the law of conservation of energy. Again, I repeat the statement of law of conservation of energy. Energy can neither be created nor be destroyed. It can be converted from one form to another. Let us understand the law of conservation of energy. Let us consider a case of simple pendulum where the mechanical energy is conserved. A simple pendulum ideally consists of a point mass called bob, suspended by an unstretchable string. The other end of the string is attached to the rigid support at the point called point of suspension. You see here, that is the rigid support, that is the point of suspension. And this is the point mass, or called the bob of the pendulum. This is the unstretchable string. When the bob is displaced from the mean position O to the point P, called the extreme position, O is the mean position of the bob. When it moves to the P, it is the extreme position, and moves to the Q, it is also the extreme position. So when the pendulum is at the extreme position P or Q, the bob is situated or located at a height h you see on both sides. In the mean position of the bob, mean position of the bob is the O. P and Q are the extreme position of the bob, and when the bob is at P or Q, it is at a height h. But this at a height h, but the speed of the pendulum is 0. Therefore, at this point, the pendulum has only gravitational energy, no kinetic energy. When the pendulum is at the position P and Q, it has only potential energy, no kinetic energy, because at position P and Q, it has no kinetic energy. It is situated, it is located at a height, so it possesses potential energy, and it is at a rest, so it has no kinetic energy. At the mean position O, the pendulum has velocity v, and its height is 0. You see at position O, at this position, at position O, its velocity is v and its height is 0. Thus, its kinetic energy, thus it has kinetic energy and no gravitational potential energy. When the pendulum is at the mean position, it reaches the extreme position as a result of kinetic energy. On reaching the extreme position, the kinetic energy gets transformed into potential energy. It means that if when the pendulum is at mean position, it has kinetic energy, and when it reaches the extreme position as a result of kinetic energy, the kinetic energy gets transformed into potential energy at extreme positions P and Q. These two form of energy transformation continuously and the pendulum keeps moving. You see at extreme position Q, velocity is 0. It means that kinetic energy is 0. Potential energy is equal to mgh because at Q the bulb is at height h, so potential energy is equal to mgh. So transformation of energy T, that is mg, potential energy is equal to 0. Sorry, kinetic energy is equal to 0, so it has only potential energy. And transformation of energy, that when it was in mean position, it has kinetic energy, and when it reaches to the extreme position, it has potential energy. It means that kinetic energy gets transformed to potential energy. And when it is at mean position O, its velocity is maximum. Hence, v square is equal to 2gh. So kinetic energy half mv square. We get v square is equal to 2gh from the equation of motion, half mv square, which is equal to mgh. So potential, since at mean position it has no height, its height is 0, so potential energy is equal to 0. So energy transformation is mgh. So total energy is equal to mgh. At extreme position P, velocity v is equal to 0, kinetic energy k is equal to also 0, so potential energy is equal to mgh. So total energy means kinetic energy plus potential energy is equal to mgh. So in all position, in mean position, total energy is equal to kinetic energy plus potential energy. Kinetic energy is mgh, so mgh plus 0 mgh. At extreme position P, total energy is equal to kinetic energy plus potential energy. Kinetic energy is 0 plus potential energy mgh, so total energy mgh. In extreme position Q, kinetic energy, so total energy is equal to kinetic energy plus potential energy. Kinetic energy is 0, so potential energy is equal to mgh, so total energy is equal to 0 plus mgh, that is mgh. So in all situations, in all positions, its total energy is mgh. So it means that the energy is conserved. The total mechanical energy in the simple pendulum is conserved. Now we discuss about power. Power is defined as the rate at which work is done. Power is the measure of how fast work is done. The rate of doing work is called power, means how fast the work is done. Let us consider an example. A man is lifting a load through a certain height in 8 seconds. The same load can be lifted by a boy through the same height in 12 seconds. In these two cases, we can say that the man is more powerful than the boy, as he has done the same work faster. Means he has done the work in 8 seconds, whereas the boy has taken 12 seconds. So we say that. So we could say here that the man is more powerful than the boy. The boy is less powerful as he has done the same work in more time. So power can be calculated as work done by time. P, so P stands for power, W stands for work done, T stands for time. So power is equal to work done into time. P is equal to W by T. The unit of power is joule per second. It is also calculated in watt. So definition of watt: when T is equal to 1 second, when time is equal to 1 second and work done is equal to 1 joule, then power is equal to 1 watt. So if work done by a machine is 1 joule in a time of 1 second, then the power of the machine is 1 watt. The power in terms of energy, since work and energy are inconvertible, therefore power is equal to energy by time. So P is equal to E by T. We express large power in kilowatt. 1 kilowatt is equal to 1000 watts, or is equal to 1000 joule per second. To express energy in household, industries, and commercial establishment, we use bigger unit of energy called kilowatt hour. Symbolically, we represent it as small k, capital W, and small s k W h. So 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second. So we say, or 1 kilowatt hour. So 1 kilowatt hour is equal to 1 kilowatt into hour. 1 kilowatt is equal to 1000 watt into 1 hour is equal to 3600 second. So which is equal to 1 kilowatt hour is equal to 36 lakh joule. So 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule. Our electricity bill gives the electrical energy we use during a month in terms of units. 1 unit means 1 kilowatt hour. A lamp consumes 1000 joule of electrical energy in 10 seconds. What is its power? Solution: power is equal to energy by time, which is equal to 10,000 by 10 seconds. That gives 100 watt. Calculate the energy of power of a pump which can lift 100 kilogram of water to store it in a water tank at a height of 19 meter in 25 seconds. Here we take the value acceleration due to gravity g is equal to 10 meter per second square. To lift the water from a ground level to a height of 19 meter, work is done against the gravity. This water work is stored as the potential energy of the water. So power is equal to energy by time. Here energy is the potential energy, mgh by t. Now substitute the corresponding value. Mass is at 100 kilogram. Acceleration due to gravity 10 meter per second square. Height is 19 meters, so 100 into 10 into 19 by 25. That gives 760 joule per second, 760 watt. Now difference between energy and power. Energy and power are different from each other in many ways. The table gives below summarize the differences. The capacity of doing work is called energy. The rate at which work is done is called power. Energy changes from one form to another form. Power cannot transform from one type to another type. The unit of energy is joule. The unit of power is watt. Energy can be stored, power cannot be stored. These are the differences between energy and power. And this is all about the chapter 4, energy. And with this, the chapter 4 is completed. And you get ready for the examination, for the half-yearly examination. Practice thoroughly all these things and be prepared for the examination. I hope you all will perform better in the examination. Best of luck for your coming examination, and I thank you for watching my video. Thank you again.